Welcome to this lecture. We are talking about the plate fin type heat exchangers, and as we know that pressure drop is equally important parameter in case of any heat exchanger. So, how do we estimate the pressure drop in plate fin type heat exchangers, that we are going to study in this lecture? And say if we look into a typical plate fin type heat exchanger, this has been taken from Case and London's compact heat exchanger textbook. You can also have a look into the fundamentals of heat exchangers by Shah and Shekulik. There you will have the detailed description or the derivation of these equations of the pressure drop. We will only look at the final expression of the pressure drop in this lecture. So, here if we look at we have this is a cross sectional view. We will find that some of the passages are blocked, where some of the passages are open and through which the flow will take place, and these are the places through which the flow is taking place and it will again come out. So, this is what is the heat exchanger core, you can say. So, this is the heat exchanger core, and we have this is the entry region where it is the header, and this is the other exit region. So, this is where the fluid is moving out, this is the entry. So, as you can understand that this flow, when it is coming and reaching to this surface or this core, it will find suddenly there is some kind of reduction in the heat transfer flow area. Earlier it was flowing through this area, now it has some reduced area because some of the passages are blocked. You may remember that we have talked about the when we talked about the construction of the plate fin type heat exchanger, we have alternative hot and fluid layer, and when this fluid is flowing through this direction, if we look into this the 3D view. So, if it is a plate fin type exchanger cross flow type, and this is the sidebar for this fluid flow, and similarly for this side you can see that this is the sidebar. So, this is when this flow is taking place from this end, you will find that it is this sidebar is blocked for this flow. So, this flow can take place only if we take this is as the frontal area. We will find that almost all a part of a 50% or some portion of the fluid flow area is blocked for this fluid. Similarly, when this fluid is flowing from this end to this end, it finds that only this passage is available for it, but it was coming from this end, it was having this much frontal area, but only this much free flow area it is having. Of course, the fins are there, fins will also block the passages, and so we can say that there is certain kind of contraction in the flow area. And on the other hand, what will happen on the exit end, we will find that the flow is suddenly getting expanded. So, as a result, we can say that we have three components in this pressure drop. One is the core pressure drop between, this is the core pressure drop between A and B, and this is if we divided it into A, B, and this is between A and B, and this is between 1 and 2. So, we have some kind of delta p between 1 and A, and then we have some kind of pressure drop in the core, which will consist of, we will come into that part, and there is another delta p. Actually, here this will be a negative one, and this will be minus B by B to 2. So, we have 3 components in this pressure drop. One is due to sudden contraction, then we have the core pressure drop, then we have sudden expansion, and there it will give some pressure rise in this region. So, here we have pressure drop, here we have pressure drop, and here there is some kind of pressure rise. So, that is what is the total pressure drop in case of a plate fin type heat exchanger. So, we have some means to estimate the sudden contraction and sudden expansion of this one. And finally, this core pressure drop, we will have 2 terms for those core pressure drop. This pressure drop, that is between core in the core, where it is between A and B, the region this between the region A and B, we have this core pressure drop. It will consist of 2 parts. One part, what we call it as the frictional pressure drop. This frictional pressure drop will have 2 components. So, one is the skin friction, and then you will have also the form drag. These 2 type of pressure drop, we form drag, these are the 2 type of friction type we will have. This is the frictional pressure drop, which will have within this one. Along with this frictional pressure drop, we may have a pressure drop due to that change in rate of momentum, and that will be taken into account. So, we finally obtain that there are 3 components. One is the entrance, one is the exit effect, one is the core pressure drop, and this core pressure drop consists of 2 parts. One is the skin friction, and the other one is the form drag. So, altogether what we find is that we have a final expression given by this one. This you will find from any heat exchanger book, or by Kazan London, or by Shah and Sekulik and others. So, here we have this delta p ratio, delta p divided by p 1. Here this is the p 1, and on this side it is p 2. So, it consists of so many factors. Here we will try to find out one by one. This is the entrance effect, where we have Kc plus 1 minus sigma squared. So, we got 2 new term here, one is the Kc, one is the sigma. Now, this sigma is basically we will find that this is a ratio between the free flow area divided by the frontal area, and this is the coefficient Kc, which takes account of the sudden contraction. And then we have another term is this is the rate of change in the momentum, or we call it flow acceleration. Then we have the core friction, as I told you that it will have both the skin friction and the form drag associated, and that will be included within that friction factor F. So, we will not separately look into the form drag or the skin fraction, both will be taken inside the friction factor F. And we have RH, RH is the hydraulic radius, and rho 1 and rho 2 are the density at the entrance and the exit end. Then we have the exit effect, where we again find 2 more terms. One is the sigma, another one is the Ke. This Ke takes care of the exit effect or the coefficient of sudden expansion. So, we have now then 4 terms in the pressure drop correlation or delta P by P 1. Earlier we were looking only into this part, we have not taken care of the flow acceleration or the entrance effect or the exit effect or this flow acceleration we have not encountered. I mean, in our earlier equation only we were talking about this delta P by P 1 is equals to this. But if we want to have an accurate estimation of the pressure drop, then we will have to take account of all this entrance exit effect, but you will find that these effects are very small as compared to the core friction, these entrance exit effects are very small. So, now we will look into the this, as we have told you that this sigma is the ratio between the free flow area and the frontal area, and we define it as AC by A frontal FR. And so, most of the time we have an idea about the what is the frontal area of the heat exchanger, and we also know sometimes it is specified. You will find that the sigma value will be given, and from there we may have to calculate the free flow area, or sometimes we have the idea about the free flow area and that 2 ratio gives us the sigma value. So, we have another term here we have encountered that is equals to the rho m. This is we have not I mean, this is a mean value, this is an harmonic mean of say 1 by rho, I mean rho 1 and rho 2, and this is given by rho m. How this is they are related to each other. So, that is why this friction factor, I mean when we are talking about the core friction, we are supposed to take this rho value, the density of that fluid at a mean value of the density, and that is basically an harmonic mean given by 1 by 2 in this equation given in this relation. So, with this information, now we will try to look into a particular problem where but before going into that problem, we need to look into an estimate of this Ke and Kc, that is the coefficient of entrance and the exit. So, this has been taken from the Case and London's compact heat exchanger book. You can have a look into that. So, here you can see that for a different kind of flow channels, this is like a channel, this is another channel where we have the flat tubes, and this is a closed cell, and we have say for the different, this is where we have the sigma value. On this side we have sigma, it is not shown here. This is where we have the sigma value. Sigma value, for different sigma value we have different Ke and Kc values. So, we can see that this whole bunch is for Ke, the exit effect, and this other, I mean dotted lines takes account of the contraction coefficient of a certain contraction. Similarly, on this side we have for the certain contraction, and this is for the Ke. So, as you can see also that we have the coefficients for I mean this Ke as a function of Re also. We have for different Re values we have different Ke and Kc. So, not only that we have the sigma on this side, we have the Ke, Kc values for different Re. So, depending on whether it is laminar or very turbulent, where I mean Re is infinite. So, between this limit we have the values of Ke and Kc. Similarly, we have for RE infinity at this one, and the other end is the laminar one. So, between this limit this Kc will vary, and between these two limits the Kc will vary for this kind of closed cell, and this is for the flat tube where we have this is the Kc and Ke values. So, if we know about the sigma value and if we have an idea about the Re values, then we can try to find out the Ke and Kc from this graph and try to estimate how much is the pressure drop due to sudden contraction and sudden expansion. But again, as I told you that this constitute or give a very small percentage of the total pressure drop. Okay. So, next we will go to numerical problem. Here we try to numerically estimate the pressure drop. This example I have taken from the Shah and Shekulik's the fundamentals of heat exchangers, and there are certain parameters or the specifications given, and we will first note them down and then try to calculate the pressure drop or try to estimate the pressure drop. First of all, for estimating the pressure drop, what we need to know what is the pressure, the fin specification or the geometric specification. Then we need to know what are the operating conditions, like what is the flow rate and etc. So, the geometric specification, I mean that what are the fin types, what are the fin details, and then what we need to know is the frontal area or the length and the width or the height of the heat exchanger. Then only we would be able to estimate the pressure drop. So, the general idea is that we need first of all the geometric specification of the heat exchanger. Then we need to look for the operating conditions. So, here for this particular one, the fin density is given. The fin density is given as fin density. What is meant by fin density? We have already talked about it, and this is having 615 fins per meter. Fins per meter. So, if we have 615 fins per meter, that means we have this kind of fin. Say this is the separating plate, these are the two separating plates, and we have this kind of fin, and like this we have. So, between how frequently they are appearing, so that is what is the fin frequency. So, from this end to this end, this is what is the fin spacing, or this is the fin spacing, or this will be, how many number of fins we have in 1 inch or in 1 meter. So, we have 615 number of fins in 1 meter, and thereby we can tell that one fin, how much is the distance between this fin to this fin. So, that is what we get an idea about the fin spacing. So, here we have the fin density, that is 600 fins per 15. So, we have 615 per millimeter. Per millimeter we have this one. Then we have the plate spacing, that plate spacing B, that is equals to 6.35 millimeter. So, we have 6.35 millimeter at the plate spacing. Then we have the fin offset length. So, as we can now understand that this is an offset, this has been given as offset strip fin, and for offset strip fin we have one, if we look at this is this is the top view. If we say this is like we have the fin arrangement, and this is what we call it as the lance length or the fin offset length. This is equals to 3.18 millimeter. And airflow length, So, the airflow length L 1, this is L 1 or sorry, this is L 2, this is L 2, this L 2 is equals to 0.6 meter. So, the air is flowing in this direction and we have it is traversing a length of 0.6 meter, and we have to find out the pressure drop due to this airflow through 0.6 meter of airflow length. Then we have the hydraulic diameter for this passage is given as 0.022383 meter. This is what is the hydraulic diameter. This has already been given, and the fin metal thickness, that is delta, that is equals to 0.15 millimeter, and as you can understand that if we are using a thicker fin, the pressure drop is going to be higher. And we have also been given the free flow area as well as the frontal area. I mean, we have already learned about that the minimum free flow area AFF, or here in this one we have defined is as FF or AC, that is equals to 0.1177 then meter square, and the free flow area by the frontal area that is sigma is equals to 0.437. We have these values given for the construction or the geometrical properties. Now, we need to look into the operating conditions. So, in the operating conditions we find that the volumetric flow rate is given as 0.6 meter cube per second. This is the volumetric flow rate V dot of air, V dot of air is given as 0.6 meter cube per second. Then we have it has already been estimated for us the Reynolds number 786, otherwise we had to calculate this one from the geometry, and the fanning friction factor, that F has already been estimated for us 0.0683. This is the fanning friction factor. The inlet pressure P1 is known as it is 110 kPa kilopascal. Then we have the inlet temperature T in is 4 degrees centigrade, whereas the exit temperature this is equals to 194.5 degrees centigrade, 0.5 degrees centigrade, and the gas constant, the R, the gas constant for air has been given as 287.04 joule per kg Kelvin. So, these are the parameters what are given for us. So, based on this information, now we have to calculate the pressure drop. So, first of all what we need to do is that as you can understand, if we look into our pressure drop expression, we have both Ke, Kc, then sigma, then we have the different densities rho 1, rho 2 and P1 is already given. So, if you now then try to I mean in our hand we have all the parameters known to us, we have to calculate them one by one. So, if we look into this we have rho 1, we have to estimate the rho 2, then we have to estimate rho m, then we need to look at the g or the mass velocity, then we need to have and look into the Ke, then we have Kc and the sigma. So, now as you can understand that we have already been told about this sigma, it has already been given. Kc, Ke we have to estimate based on these sigma values. So, depending on the sigma values and the Re value, we have to estimate this Ke and Kc, and then we have to estimate rho 1 and rho 2, and based on this rho 1 and rho 2 we will estimate this 1 by rho m as 1 by rho 1 plus 1 by rho 2 is equals to 1 by rho m. So, from there we will calculate the rho m, and then we have to estimate G. We have been given about the mass flow rate, the volumetric flow rate is given. So, from the volumetric flow rate we will multiply it with the density, appropriate density, to get the mass flow rate, and we also know, we have already been told about the free flow area. So, we can estimate the value of G, and then we can calculate the total pressure drop. So, if we look one by one into those parameters now, if we will find that rho of the inlet can be estimated as a function of I mean, if we assume it to be an ideal gas, we can use the PV inertia relation. So, this is P air in the by R T A inlet. So, you have to convert this A into the Kelvin, and accordingly this will come out as 1.3827 kg per meter cube. So, this will be the density of the air at the entry. Then we can similarly calculate the density of air at the exit, and we will have to assume some kind of pressure drop, but we do not have the pressure drop idea, but it is I mean, we need an assumption at this point, and we will assume that the pressure drop is not substantial. So, that we will use the same pressure drop relation, I mean that 110 kilopascal, and then later on we have to rectify ourselves if we are getting really a very large pressure drop. So, we will put this value of 110 kilopascal here, and this R value already we have told, the temperature is already known. So, accordingly we will be able to find that this is coming as 0.8195 kg per meter cube for the density of the exit air. So, based on these two values of rho inlet and rho exit, we can then calculate the rho m. This will come out as 1.0291 kg per meter cube. So, this would be the mean density, and then we have the G. G can be estimated from the volumetric flow rate multiplied by rho at the entry, and then we have the free flow area as we have estimated, that already it is given. So, from here we would be able to calculate the G value or the mass velocity 7.086 kg per meter square per second. So, that is the unit, and for the Reynolds number given, we can try to estimate the calculation. I mean, we can estimate Ke and Kc. So, the figures that we have given are shown there. From there you would be able to find out that Ke is coming as 0.33 and this Kc is given as 0.31. So, then we put all these parameters now are known to us. So, accordingly we can try to find out that delta P by P1, and this will come out as 0.01536. So, we can find that the pressure drop is 1.69 kilopascal, and that is not really a very I mean it's not on, it's only about 1.5% of that total inlet pressure. So, that the assumption that has been made in our calculation that the exit pressure is not really very different from the inlet one is valid, and we can I mean use that assumption for, we do not need any separate iterative calculations to repeat this one or to estimate the exit pressure drop. So, this is how we calculate the pressure drop in a plate fin type heat exchanger. So, we have already talked about it. Thank you for your attention.